All right, this is module number 34. After we started discussing linear classifiers, we're now going to go to linear discriminant analysis and quadratic discriminant analysis, LDA and QDA. So this is essentially a Bayesian approach to classification. Consider fk of x being the posterior densities, the density of the data x conditioned on the label k, and the class K has some probability. Every class has a prior, pi k, which is non-negative, and the sum of the priors, the sum of the pi k's, sum to 1. And Bayes' theorem informs us that the probability that conditioned on observing data x that we're in class K is in the numerator we have the probability of x appearing jointly with k. And in denominator, we're summing over all the k primes, not necessarily k, but including k, all the k primes from 1 to capital K, the total number of classes, over the, again, joint probability of x with k prime. Now, what is probability of x occurring jointly with k? It's pi k, the prior, multiplied by the density of x conditioned on k. So we have in the numerator pi k multiplied by f of x given k. And in the denominator, again, this would be k prime. We're summing over all the k primes, pi k prime multiplied by the posterior of x conditioned on k prime. And we denoted that fk of x is the posterior density of x given k, and therefore we have finally pi k fk of x in the numerator, summation over, again, k prime, pi k prime, fk prime of x in the denominator. So sounds good, sounds simple. Well, maybe not very simple, but 3-4 lines of math, that's reasonable. But we need a statistical model for the posteriors, and that may require some work. All right, so let's look at an example of how to use this approach. And this is a practice midterm from 2016. We have two classes of data, blue and red. Each of them has prior p blue equals p red equals 0.5. So let's gradually jot down the fact. So pi b is the probability of blue. It's equal to pi r, which is the probability of red, and it's equal to 0.5. Now, f blue is that given that we're in the state in the class blue, the data x is half of the time it's Gaussian, centered around mean 0 with variance 1, and another half the time it's Gaussian, centered around mean 2 with variance 1. So let me illustrate this in a combination of black, blue, and red. The horizontal axis will be the value of the data x. The vertical axis will be f of x, and we have two f of x's for k, the class being red or blue. So now let's do red. So with red, I am Gaussian, 0 mean, variance 1. So the 0 is at the origin. And let's say that this is my Gaussian blob. Now what about blue? I have two Gaussian blobs centered around -1 and +2, but note that their amplitudes are half. So the peak of these two blobs is somewhat lower, -1 and +2. Here we have a Gaussian blob, and here we have a Gaussian blob. So two Gaussian blobs. As I said earlier, the means of the Gaussian components are different. The variance of all the components, to keep it simple, are 1. And this is possibly a point to revisit. What about if we have different variances but the same mean? That's also a point to revisit. And additionally, the probabilities of each pi b and pi r are also equal to half, which is perhaps something to revisit. So we can revisit these assumptions later. But for now, let's derive a Bayesian classification approach. So I want the probability of being blue conditioned on the data x, all right? So this is in the numerator, we have the joint probability of B occurring with X, but here's the thing. There are only two possible classes, blue and red, therefore I wrote probability of blue. These are probability masses for blue and red, but X is continuous value. Therefore we have in the numerator f of B occurring jointly with X, and in the denominator, I have a summation over the k's, f of k occurring with x. And recall, k is either blue or red, okay? So nothing complicated here. So let's continue this derivation. And I'm gonna write quite a lot, perhaps multiple versions on one line because we don't have that much space. So I hope this will be readable. So in the numerator, I have f of b comma x, and in the denominator, I have f of b comma x, b for blue, and f of r comma x, r for red. Now, what is f of b comma x? It's the prior for b. So in the numerator, I have, let's call it pi b, PIB, or actually pi underscore b, multiplied by f of x conditioned on b. And earlier we had f blue and f red. That's what I'm going to plug in soon. Divided by, I'm going to copy this expression. And I have the same expression with blue and the same expression with red. Now, I'd like you to note that PIB equals PIR, just remove from denominator and numerator. So we have f of x conditioned on blue divided by f of x conditioned on blue plus f of x conditioned on red. This is equal to, now we can finally substitute. So this is going to be f of x for the blue is half multiplied by a Gaussian blob centered around -1 with variance 1. So I'm dividing by square root of 2 times pi times 1 multiplied by exponent of minus x minus its center is -1 square divided by 2 times the variance. The variance is 1. My second term in the numerator is half divided by square root of 2 pi. Same thing because I have a Gaussian PDF with variance 1. Exponent of, now instead of -1, I'm centered around 2, and I have the same variance as before. Now we have a long denominator. So numerator plus. For the blue, I don't have the half anymore. I have a single Gaussian component, 1 over square root of 2 pi times 1, exponent of the, so recall the blue, I had two components, each with probability half, centered around -1 and 1. For the red, my single component is centered around 0, so x minus 0 squared. And this is equal to, so now let's think about it. So let's again note all the square root stuff is the same, can remove. So I have half times exp of minus x plus 1 square over 2 plus half times exp of minus x minus 2 square over 2. This is going to be my numerator. And in my denominator, I have all the above, plus, without the half, I have exponent of minus, well, x minus 0 squared is x squared over 2. That's it. And now, some of you may not be clear. Okay, so I have a probability for b given x, probability of red given x, plus the probability of blue given x is equal to 1. That means that the probability of red given x is 1 minus the probability of blue given x. And that means that I have the same denominator as before. And my expression in the numerator is going to be exponent of minus x squared over 2. How do I actually run the classifier? So I have a probability for B given X. I have a probability for R, blue and red, given X. I run the classifier by calculating these two probabilities and presumably choosing the larger one. Why presumably? You might ask, hey, why would you possibly, if the probability of blue given X is larger than the probability of red given X, why would I possibly choose red? Well, what if for some reason, some types of mistakes are more costly than others? If some types of mistakes, so let's say that blue corresponds to you're healthy and red corresponds to you have coronavirus. So we probably if you're red, we don't want to mistake if you're red. So we don't want to incorrectly estimate blue if you're red. We really don't want that. But on the other hand, if you're healthy, you're blue, and we mistakenly classify you as red, that's unfortunate. You need to quarantine for 2-3 days until we retest you, but it's less of a problem than if you go and infect 20 people. All right. So hopefully that's clear. So now let me clear everything. And as I wrote, we worked that out. There are detailed solutions in the supplement, but I also want to revisit these points. In my example, the means of the Gaussians are different. But what if I have two means that are same, in particular with different variances? So here, I might have the following situation. The horizontal axis would be x. The vertical axis would be f of x. And imagine that the red blob would be a wide Gaussian blob. So FR would be n, 0 mean, and variance, let's say 4. 4 meaning that the standard deviation is 2. And now let's have a blue blob, which is higher but narrower. So FB is n, 0, 1. The standard deviation is 1, the variance is 1. The blue blob is 2 times narrower. I don't know if I sketched the scale, but I at least tried. 2 times narrower than the red blob, but it has to be 2 times higher, okay? Now, if you think about it graphically, at this point and at this point, in this region, the blue is larger. We will decide blue. And in these regions, we will decide red. So if the variances are different, we could have this interesting thing that we have more than 2 regions. Now, what about if the probabilities of the blue and the red are different? So let me again make a sketch. As before, horizontal axis is x, vertical axis are densities, densities assuming red and assuming blue. So what if our red, or you know what? Let's imagine again, blue is you're healthy, red is coronavirus. Imagine that very few people are sick, okay? Very, very few red. So blue, and let's imagine that X is your viral load. So blue is gonna be a low viral load and a lot of people. And red might be a high viral load, but because very few people are sick, very low height. So it could be that our cutoff, here we're going to decide R, here we're going to decide blue. And in this region, the red is higher, in this region the blue is higher. And again, I said that maybe the penalty for having a person who's sick, red, and that we incorrectly decide blue, maybe the societal penalty is severe, maybe the societal penalty for the opposite. You're healthy, we quarantine you for a day or two until we retest you. Maybe that's manageable. So in that case, we may want to shift the threshold, move it toward the left. Okay, so this is an extended example with different variations, and you can see that Bayesian classification can quickly become interesting. So a big question is, what's the posterior model? If we know the density of x given k, we're done. But that's a big if. In many applications, maybe we have an approximation for that, or maybe we're trying to estimate it from the data. So what are possible approaches? One approach is that we'll use Gaussian densities, and that leads to linear discriminant analysis, which we will describe soon. Another approach, which appeared in my example, is a Gaussian mixture. Either the blue or the red, I don't remember, had 2 Gaussian components. And because of that, when you have multiple components, the decision boundaries can become more interesting. Another possibility is to have a non-parametric density. Instead of having Gaussian or Gaussian mixture or something, it's completely non-parametric approach. And finally, in many applications, the data is multidimensional, and naive Bayes assumes that the probability density function is separable, meaning that for each of the dimensions, the probability along the different dimensions is unrelated. Now, the word naive sort of gives this off. This is naive, it's imprecise. However, when we're dealing with high dimensional data, oftentimes making this naive assumption is better than basically overfitting. So let's chat just a bit about multivariate Gaussian distributions. So we can choose a multivariate Gaussian density, fk of x. So by multivariate, I mean, just to make it clear, multidimensional. So the dimension will be p, all right? And earlier, when p was equal to 1, my Gaussian density, I had a term 1 over square root of 2 pi times the variance. And the variance is often denoted by sigma square. And now the 2 pi, we're taking that to the power of p. P is the number of coordinates, the dimensionality. And this notation, the brackets around the sigma k are the determinant of a matrix, and sigma k is a covariance matrix. Covariance matrix sigma k. Now, you can go read about it in the book. In a nutshell, this covariance matrix, for every 2 dimensions, it captures the possible dependence between the elements along those 2 dimensions. Okay, so entry ij in the matrix captures the covariance between elements I and j. So the first term of the Gaussian PDF for p equals 1 you've seen before, and the second term we've seen exponent of minus half x minus the mean, which can be denoted by mu square, divided by 2 sigma squared. So what do we have for this latter exponent term in the multivariate case? Negative half is the same negative half, so I'll put a check mark. Instead of x minus mu square, so this is a multidimensional type of squaring operation. So we're taking x minus mu k transpose. The k is for class number k, and x is a column vector. Mu k is a column vector. So column vector minus column vector is equal to column vector. Transposing it, I'll put a t over the arrow, gives us a row vector. Note the sigma k inverse. The inverse is why we divided by sigma square earlier. And by the way, I now note that this 2 and the 2 and the negative half, the 2, they were redundant, so I only need a single 2. Dividing by sigma square is similar to multiplying by the inverse of the covariance matrix sigma k. And the covariance matrix, which was square, its inverse is also square, p by p. And finally, x minus mu k is a column matrix. So we have a row matrix times a square matrix times a column matrix. Square matrix times column matrix is column matrix, and row times column is scalar. So all of this stuff is a scalar, and it essentially gives you the quadratic relationship between x and mu k, where we normalize each dimension basically based on the covariance matrix. Now, in some cases, we're going to assume that the Gaussian densities for each of these classes k is going to be the same. In other cases, we're going to assume that they're different. If they're the same, then if you think of a contour plot where the PDF the PDF takes on the same values, imagine that this would be at p equals 2. This would be coordinate x1. This would be coordinate x2. Suppose that mu would be over here. And now the contours might be something like this. So angular ovals surrounding mu. So in some cases, we're going to assume that all the sigma k's are the same. In other cases, we're going to allow them to be different. So here's our interpretation again. We have a Gaussian blob centered around mu k. The elliptical level, the contour is where the Gaussian densities are the same. The structure of the ellipse, whether it's angular or not, whether it's a thin ellipse or a thick ellipse, even a circle, all of these depend on the covariance matrix. And here we have an example where the 3 sigmas are the same. It boils down to 3 linearly separated decision regions. So LDA, or linear discriminant analysis, we can show that the probability of being in class K conditioned on the data X divided by the probability of class L given the data X is first we taking the log of pi k divided by the log of pi L. That's a constant. And then we're taking the exponent terms, the log of the exponent, what's inside the exponents is turns out to be half of mu k plus mu L transpose times sigma inverse times half of mu k minus mu L, so minus sign plus sign. And note that this is independent of x. Or in other words, it's a constant. And now I'm going to shift colors. Here we have x transpose multiplied by sigma inverse multiplied by mu k minus mu L. Now, you'll note that x transpose is basically multiplied by a matrix. And because it's multiplied by a matrix, this log likelihood is going to have a linear form, all right? And because it has a linear form, we get a linear decision boundary. For example, this could be the decision boundary. On this side, we decide 1. On this side, we decide 2. So how do we run the classification? We have a linear discriminant function, delta k of x, which we don't necessarily need the log likelihood. We don't need to divide by g equals L over x. We just need the log of the probability for k given x. And we choose the k that maximizes delta k of x. This is equivalent to choosing the k that all of the terms that we had earlier for that k, the numerator is larger than the denominator or greater than or equal to the denominator, meaning that we're taking the log of something that's greater than or equal to 1, and thus the outcome is greater than or equal to 0. So we're choosing the k that either maximizes this discriminant function or alternately, the log likelihoods are non-negative. In practice, of course, we're not necessarily given the covariance matrix. We're not necessarily given the means of the different classes and their priors, and we're going to need to estimate these from the data. Now, because we end up with linear decision boundaries, it can be shown that linear discriminant analysis is quite related to a linear regression approach for classification, and you can read some of the details in the book. And now, QDA, quadratic discriminant analysis. In LDA, we're assuming that the covariance matrices are the same. Let me go back to the previous slide. When they're all the same, we had the same sigma inverse here. When they're different, each class has a different elliptical set. And when different classes have different elliptical sets, the decision regions are no longer lines. They can become quadratics. QDA requires more parameters than LDA. Not only do we need to estimate one covariance matrix, we need to estimate all the covariance matrices, one per class. To get this to work reliably, we need more data. We need a somewhat larger N. And in general, both LDA and QDA have good performance. The issue is that although they support a single Gaussian blob, a single multivariate Gaussian density, the data, especially when you're talking about a larger P, a larger dimensionality, the data seldom supports complicated decision rules. And because of that, LDA and QDA that happen to have somewhat robust, somewhat stable boundaries, often on higher dimensional data, they're better than some complicated rule. So that'll be it for the module on LDA and QDA, and we'll continue next time.